Hello, everyone. Thank you for joining the GeoScience and GeoEnergy webinar of 3rd of September 2020 today. I hope everybody is happy and safe and enjoying the start of the academic semester also. Sebastian Geiger from Heriot-Watt University and myself are pleased to host you again this week with yet another exciting talk around the subject of geoscience and geoenergy. Please also subscribe to our channel. It would make it so easy for you to get the announcement of the upcoming talks. Also, junior researchers, please notice a Tea Time Talk series has been established to let you disseminate your research, get connection, network, and share your research as well. Now, without further ado, I would introduce our keynote speaker of this week. It's my pleasure and honor to introduce to you all Professor Chris Spiers is our keynote speaker of this week. Chris is emeritus professor at the High Temperature and Pressure, or HPT. If you noticed, I said temperature and pressure, but it's actually pressure and temperature. So that would make you all remember that. So it's high pressure and temperature HPT lab at the Faculty of Geosciences at Utrecht University here in the Netherlands. He led the group as professor of earth materials until retirement just recently in March 2020. He specializes in experimental rock and fault mechanics at crustal and uppermost mantle conditions. His work is hallmarked by a focus on the effects of fluid-rock interactions and the microphysics of deformation phenomena. Quite a challenging yet very, very hot topic in the geoscience community. Chris was born and educated in the UK, so Sebastian's side of the border, and he gained his Bachelor of Science degree and a PhD from Imperial College in London. Following his appointment as a Miller Research Fellow at the University of California at Berkeley, for about 2 years, he moved to the Netherlands, to Utrecht University, where from 82, he has built up the HPT, the lab that I mentioned earlier in my introduction. In his 39 years at Utrecht University, Chris has worked on topics ranging from the rheological and transport properties of evaporites, carbonates, and olivine rocks, with emphasis on fluid-assisted deformation processes to the creep and frictional behavior of seismically active faults, and to the mechanical behavior of reservoir rocks, cap rocks, coal, and shales. In the last 10 years, much of his work has been in the context of CO2 storage, natural gas production, and induced seismicity, as in the Groningen giant gas field. I'm borrowing the word from his title, actually a very attractive title for the talk. Chris gained his chair at the Utrecht University in 92. Since 2010, he holds a parallel chair at the China Earthquake Administration's State Key Lab for Earthquake Dynamics in Beijing. I'm very curious to know if he can speak Chinese, by the way, but I'll ask him maybe in the discussion session. He has served as Dean and Education Director in Earth Sciences at Utrecht and played a leading role in the university and national research programs on georesources, CO2 storage, and sustainability. Chris has published more than 200 peer-reviewed papers and book contributions. In 2017, he was awarded the European Geosciences Union NEEL medal. Thanks a lot, Femke Fossepol, for correcting my pronunciation of NEEL. I used to call it NEEL, but I found it NEEL medal for his contribution, significant contribution to the field of earth materials and rock physics. Chris, it's our pleasure and honor to host you this week. Thank you very much for accepting kindly our invitation To the audience, please note Chris' lecture would last for about 35 minutes, and then, like always, followed by discussion session that will be chaired by Sebastian. And please do not wait till the end of the talk. Post your question whenever you think appropriate, because that might also trigger other questions from other participants' mind as well. Chris, the stage is all yours.
Thank you very much, Hadi. Thank you for the very extensive introduction. Makes me feel a little older, but it's all fine. Let me say good afternoon, good evening, good morning to everyone who's listening. It's a great pleasure to be able to contribute to this webinar series which Hadi and Sebastian have set up. It's a great series. I'm going to talk indeed about the rock and fault mechanical controls that influence induced seismicity in the Groningen gas field in the Netherlands, a very, very large gas field. Many of you who are listening from the Netherlands will have heard parts of this talk or most of this talk before, but many of you are not in the Netherlands and some of it will be new. So I'm going to start with an introduction to the field itself. So here we go. The Groningen gas field. Here it is. It's a very large gas field in a relatively small country. The Netherlands is quite a small country. The Groningen gas field is the 7th largest onshore field globally, viewed in terms of the initial resources. Even now, after it has about 20-25% of the gas remaining in there, it's still easily in the top 20, in top 15. It's a huge gas field. It was discovered in the 1950s. It's been producing since 1963. Seismic activity has started there, and it's likely to be shut down pretty soon because of the effects. It's operated by a company called NAM, a joint Shell Exxon venture. A very, very large field with which has had huge economic importance for the Netherlands. It's one of the few very large fields which has been producing so long worldwide. Now, where is all that gas? It's in the sandstone, the Slochteren sandstone reservoir. Here it is on this geological section, the green and the blue. That's the Slochteren sandstone. It's a Permian, Aeolian, or alluvial fan sandstone, typically about 100 to 200, 250 meters thick. It's located at about 3 kilometers depth, so it has an overburden pressure, vertical stress of about 65 MPa. The original gas pressure was pretty much hydrostatic, 35 MPa. It's reduced now to about 8 MPa here in the pores of this sandstone reservoir. It's overlain by a claystone and a very thick packet of Permian evaporites. The source rock is the Carboniferous, which lies below an unconformity here, which contains some coals. That's the source of the gas. All right, so this section is northwest to southeast, you see here. So that's where the gas is. What have been the effects of production of gas from this reservoir since production started in 1963? Here's the field again. Of course, there has been some subsidence, and that subsidence has progressed reasonably steadily with time and with depletion of the reservoir pressure, and it's now reached somewhere around about 35 centimeters of subsidence in the central part of the subsidence bowl. And here you see that inverted into compaction in the reservoir. So this is where you see most of the compaction occurring in the reservoir. Okay, so subsidence, one of the most obvious direct effects of gas production. But there have also been earthquakes occurring. In the early years, when production was very, very high initially, there was no seismicity. But right at the beginning of the 1990s, earthquakes started to be recorded. And the event frequency has increased since then, up until somewhere around here in 2012, there was the largest earthquake which has occurred so far, magnitude 3.6 at Hausinger, which seems very small to people who come from countries where you have natural earthquakes. But this is a man-made event here where we don't have earthquakes in the Netherlands, and has caused a lot of societal concern. So this is actually quite a big problem for the Groningen field. And you see here in 2012, when the biggest event occurred, very soon after that gas production was reduced, and there has been a reduction in seismic activity since. The earthquakes, represented here by dots, and here the magnitude represented with the red blobs, the earthquakes are very definitely concentrated in the regions with the maximum subsidence. So, where exactly these earthquakes are occurring? The latest data from obtained from expanding the seismic network has shown very clearly that these are associated, the earthquakes are associated with ancient fault systems that cut the reservoir. Here we are. So this is zooming in on the field. Here you see the massive number of seismometers that have been placed there by NAM since the large earthquake in 2012. So very soon after, just a couple of years later, enough data had been collected to locate the earthquake events more accurately, and they very, very definitely line up on these fault systems that you see here, which cut the reservoir. Most of these earthquakes are actually centered pretty much in the reservoir or above it or just below it. Okay, so the cluster around the reservoir itself on faults. Right, so after this large earthquake in 2012, NAM, the operating company, started a huge research program to investigate exactly how this was all working. And they approached us and asked us to take on two projects. One to study the compaction of the reservoir sandstone, and the second one to look at the activation of these faults, to try to understand the dynamic behavior and failure of these faults that are cutting the system. Of course, data on that is really important for any kind of numerical modeling for evaluating risk and the field behavior. The focus for us, we were asked to try to understand what are the physical processes actually operating in this system under real in situ conditions, real processes under in situ conditions, controlling compaction, controlling fault mechanical behavior, fault strength. So we're an experimental lab. We sort of brought in stuff like this to try and address these issues. I shall skip right over it. Most of the work was done by PhD students and postdocs, of course, and my colleagues. I have to say that, you know, they did really everything. Please read their names carefully. So the reservoir compaction, let's start with that. Of course, if you start producing natural gas from reservoir schematically represented here, then the reservoir is going to start to compact because the vertical effective stress is increasing. What does that do? Well, of course, you have a deformation field set up in the sandstone, and where you have offsets on faults and so on, you get gradients. So you set up stresses around these faults which can tend to activate them. You may reduce the normal stress, increase the shear stress, and therefore enhance the potential for the faults to be activated. So the compaction response of the sandstone is directly involved in determining the stress strain field around these features, and is important in part as part of the driving mechanism for the earthquakes. How does the sandstone behave is therefore a crucial question. Of course, the sandstone will be partly poroelastic. There'll be elastic compaction of the sandstone. There could also be inelastic or permanent deformation. And a key question for understanding the stress strain field, the energy stored in the deforming system, and whether or not faults are going to be forced into motion, right? A key question there is, what is actually the partitioning between elastic deformation and inelastic, permanent plastic deformation going on in the reservoir. This is what we try to investigate doing compaction experiments. Right, well, you need samples to do that, and the company NAM provided us with fantastic core material from a well that they drilled in 2015. The samples were taken from a location here, near here, in this part of the field. You see it all happening here. It's a fantastic effort, drilling into a highly depleted reservoir. It was a very tricky operation. They were successful, recovered a full set of core from the reservoir and material just around it. So that was a fantastic effort, gave us wonderful samples along with samples which came from exploration boreholes before the field was actually depleted. So we had material from before depletion and after depletion. We have done many experiments, triaxial tests on these sandstones, on the so-called Slochteren sandstone, from these different locations, 2 locations, the one drilled in 2015 and an earlier one from 1965, just before that part of the field was depleted at Stedum. We've done lots and lots of triaxial compression tests, stress relaxation tests to look at the rate effects, and many tests where we've hydrostatically stressed cycled the samples followed by axial stress cycling, and you'll see why in a moment. We've investigated a wide range of porosities of samples from the field, from the lowest values that you encounter, around 12%, to highly porous samples, 26%, at reservoir temperature, which is about 100 degrees, with a true pore fluid, a simulated pore fluid, but with very similar composition to the real thing, highly saline, and we've explored effective confining pressures that span the complete range of conditions that would be relevant. I want to focus on these stress cycling tests that I mentioned. So these actually really what I feel are really spectacular results. Have a look at these 2 samples here. These are what we call 2 twin samples. They're samples of sandstone poured directly adjacent from each other, normal to the bedding of the sandstone reservoir rock, from the same piece of core recovered from the borehole. Okay? And these have been deformed for the purposes of assessing, okay, well, how similar do they behave? Now, I want you to focus first on this sample, which is the black lines, okay? So what we did with this sample was we subjected it to hydrostatic stress, which we cycled. So we loaded, unloaded hydrostatically, loaded, unloaded, loaded, unloaded, until we got up to our best estimate of the present lateral stress. So this would be, in effect, the present a hydrostatic stress representing more or less the present state of stress. Okay, so it's expressed as mean effective stress. These are hydrostatic load cycles, and what you clearly see is that you have permanent deformation occurring at every stage. Once we reached the hydrostatic condition, we maintained the radial stress constant, and then we loaded the sample axially with a differential stress, again cyclically. Load, unload, load, unload, load, unload. And again, you see more or less linear envelope here, which is quite different from this strongly curved envelope. You still see this permanent deformation is accumulating, and in effect, every time you reload the sample, you reach a sort of a yield point, and then you go to a higher stress. By the time we got to these kind of stresses, you start seeing the sample is starting to fail. Okay, and this is unloading. Now that's the black. Those are the black curves. What about the red curve? The red curve is this sample, which we loaded monotonically. And to our surprise at the time, and this occurred in many experiments, we found exactly the same envelope. So what you can see from this is that this load cycling behavior does not actually influence behavior of the sample. Sample undergoing this load cycling behavior behaves exactly like an intact sample. And so that really means that each of these reloading steps accumulates permanent deformation, and when you indeed reload, you start a new phase of permanent deformation, which is maintained when you unload the sample. So each of these points on the black curve here at the peak of reloading is in effect a yield point. So this is describing a hardening behavior involving permanent deformation of the sample. And you can see the amounts of permanent deformation here that are occurring compared with the unloading curve, which is elastic, are large. So what can we say from this? We can say that load cycling gives you the same mechanical behavior in terms of mean effective stress against porosity reduction as a monotonically loaded sample. Right? So the porosity reduction was measured from the internal pore volume, fluid volume change. So this stress strain behavior is not affected by this cyclic loading. It means we can use it to represent the behavior of the sample. And we see that in each cycle, we're getting 30 to 60% of the total strain, notably in this portion, 30 to 60% of the total strain is inelastic. It also means that 30 to 60% of the mechanical work done in deforming the sample is actually dissipated. It's not stored as elastic energy. That's important because this linear behavior, of course, if you just look at this linear behavior with a single sample without doing load cycling, you might think it's some sort of elastic behavior, but it's not. It's linear, and it's a combination of elastic and inelastic behavior, with the inelastic deformation, being around half. It's a very large effect. Okay. Now, if we compare this with sort of the literature, there are many reports of this kind of shape curve in the literature, which we also found with this linear part here. Most previous work that's been done on trying to obtain constitutive relationships for inelastic behavior of sandstone is focused on this regime here, stage 3, approaching failure, okay, where grains get crushed and so on. The early stage 1 down here, well, we have very strong evidence that this is, in fact, closure. This corresponds to the closure, compliant closure of cracks that are already present in the sample due to removing it from the subsurface and preparation and everything else. And this region, this stage 2, this linear behavior, this starts when you get roughly to the in situ stress. So you've closed all the damage you introduced into the sample, and this is the in situ behavior that you want to get from the sample in that case. So here it is then. This is very frequently, this type of behavior is very frequently assumed to be poroelastic, but what we've shown in these experiments on the Groningen material is that, 30 to 60% of this is inelastic. Right, now where do we go from there? What can we say then for stage 2? This is the stress range that is relevant for the field, for the gas field in Groningen. It's a linear behavior, but we don't actually have a nice description of this combined elastic and inelastic behavior. We don't know what the mechanism is, what is happening here, what is actually controlling this, what physical process is controlling the inelastic behavior going on here. Well, to describe that behavior and get a constitutive model for a start, what we did was we simply conducted a whole bunch of these cycling behavior, where we brought the sample to a hydrostatic stress, and then we cycled the differential stress to higher and higher values. And here you see these streams of points here. These are individual cycling tests. And in effect, each little dot in these streams of data represents the top of a cycle. So the yield point where you start accumulating more permanent strain. And at each point, we know the porosity of the sample. So what we can do is make a contour map in differential stress against mean effective stress space. We can make a contour map which essentially shows the strength of the sample at different values of porosity reduction. What you clearly see then here, right, porosity reduction 0.1%, 1.2%. As you compact the sample, then this yield envelope, and that's what it is, of course, in this differential stress versus mean effective stress space, this yield envelope expands. This particular one is for a sample of 13% porosity. By the time you get to 21% porosity, you see similar behavior, but it's much weaker. The material is much weaker. At 26%, it's much weaker again. So between 13 and 21%, actually around 20%, there is a very large reduction in the strength of this sandstone. Now, what we could do was we could fit a CAM clay model, which is a sort of standard constitutive model for compactive materials, to this data. And for the stage 2 behavior, which is the right stress and strain range to be relevant to the gas field, to production of gas, the CAM clay model actually fits this data pretty well. I'm not going to go into detail about that, but we obtained a reasonable fit of the CAM clay model to this data in this stage 2 region. And with this M parameter, which is simply one of the parameters in this CAM clay model, we managed to get an empirical description of how that depends on porosity. So we have a constitutive model for the sandstone at real in situ conditions, which is porosity dependent, with a very, very big change in the strength of the sample, if you like, at about 20%. Okay, so we could describe how the sandstone behaves. In effect, what we did by fitting this CAM clay model was have a description of the plastic deformation of the sandstone and an independent description of the elastic part from the unloading behavior. Putting those together gave us a full elastic plastic description. But what controls it? What are the physical mechanisms actually controlling compaction of this sandstone? We did experiments in the synchrotron, which helped us to gain information into this in Grenoble. But in the end, a much simpler kind of experiment gave us the highest resolution images of what's actually going on, and in fact told us the most. What we did was we took a cylinder of this reservoir sandstone, we cut it in half, and we made very, very detailed images using electron microscopy of the surfaces of this. We reassembled the sample with very thin layers of polymer or other soft materials in between the sandwich, and we deformed the thing under exactly the same triaxial conditions that we did our other experiments. So if you again look at this mean effective stress against porosity reduction curve, here you see the curve stage 1, stage 2, stage 3. Stage 2, this is the stress and strain range or porosity change range, which is relevant for the field with the linear behavior. But what we did was we simply took, for a single sample, we examined it here, we deformed it, we took it out, we examined it again, we deformed it again, took it out, and so on. And by comparing the images obtained at different points, we could actually see what is going on in the sample. Now, I'm going to show you the results that were obtained for this point, so just at the onset of the linear behavior, which is relevant for the field, where we know you start to get this inelastic plus elastic behavior. So I'm going to show you an image of before stage 2, right at the end of stage 2 deformation, which is this is the range that's relevant for the field. Okay, so this is at the onset of stage 2. You see quartz grains in the sandstone here, and you see clay films, which are very common throughout this huge reservoir. These are very, very widespread. You see clay films coating the grain contacts. Now watch what happens when we deform this in stage 2. Right? You see it? You see that the clay in the boundary compacts. So I'm going to try and go back and do that a few times. Before, after, before, after, before, after. If you focus on this bit, before, after, you can clearly see that these clay films are compacting, and that is what is actually accommodating the inelastic strain in this reservoir rock. The grains are not breaking. Is that what goes on in the reservoir itself? To find out that, what we did was we examined the microscopic structure of samples that were taken from core retrieved before production started, and we compared those microscopic structures with those seen in samples taken from the core that came from 2015. So 50 years of production in between, before production and after production. And what we did was we measured crack densities within the quartz grains. This is schematic. Measured crack densities against porosity for the blue points are before the field was depleted. So these come from samples that had the full original gas pressure. And the red ones are samples from 2015, where there'd been 50 years of gas production. And this crack density against porosity, there's no difference between these two distributions. What we found was all of these samples from both sources have microcracks in them, which are totally indistinguishable in any way. So, in fact, there is no effective depletion on crack density. That means that it's not cracking in the grains that causes deformation in this reservoir. And the only remaining hypothesis is that it is indeed these clay films which are getting compacted. And that's what we have very strong evidence that that is the mechanism that causes this inelastic deformation. So what? That means we have a different constitutive model, then a new constitutive model for the behavior of the sandstone. And you could, that linear behavior that's relevant for the reservoir, you could fit it with an assumed elastic behavior, and you could fit it with our elastic plus plastic CAM clay model. That's what we did. And we used those two models, so our assumed elastic model versus our CAM clay plus true elastic behavior. We used these two models to predict how the horizontal effective stress would vary in the reservoir, would increase in the reservoir as pore pressure is depleted, as gas is produced. So for assuming that the behavior we saw was elastic, then you see this increase in the horizontal effective stress, high porosity at low porosity. Okay, and there's a bit of uncertainty about the initial effective stress, so it would be somewhere in this range. These points here are measured in situ stresses. So you see this, if you were to assume that that linear behavior was elastic, you can't actually match this data that you see in the field. If you take this inelastic behavior combined with true elastic, so our constitutive model, what you see is that samples with the higher porosity, above 20%, they show much larger horizontal effective stress development, which corresponds a lot better with the measurements in the field, which incidentally come from a region where the sandstone has a porosity of 19%. So what we believe here is that our results are giving a much better constitutive description of the way the sandstone behaves, and so that model should give a better description of the stress-strain evolution in the reservoir around faults as depletion occurs. So it should be a better basis for modeling the behavior of the sandstone. We also have put that model into fault rupture models. And I don't have time to go into this in detail, but essentially what happens, besides influencing the compaction behavior of the reservoir, the slip behavior on faults when they are reactivated is also influenced, of course, by the behavior of the reservoir. And what you see here is that if you were to assume the reservoir is elastic, you get this slip patch. This is a measure of the final shear displacement on a fault. Here's a fault schematically shown. When you actually take into account the real constitutive behavior of the reservoir, you get a smaller slip patch with less displacement. So it influences the earthquake generation behavior, if you like. I'm going to immediately skip on to talk about faults now. So what have we done on faults alongside this work on the reservoirs? We try to understand how strong are faults, and once you reactivate them, how are they going to behave? So, of course, the strength of a fault can be represented by something like a Coulomb envelope. That only tells you when it fails. It doesn't tell you what it does thereafter. In order to know whether you're going to get an earthquake or not, you need to know if you can have some sort of weakening with displacements or slip weakening behavior, or whether you have some rate and state type dependent behavior where you get velocity weakening. The faster the fault goes, the weaker it gets, which can also give you instability, of course, can give you an earthquake. So what we did basically, here's an enlargement of the stratigraphy around the reservoir. Here's the sandstone. Here's a typical fault offsetting the reservoir by, something in the range of 20 to 50% of its thickness. That's typically what you see. And below there are these carboniferous source rocks, shales and siltstones, clay-rich, very clay-rich Tendur claystone rock here. And this is an anhydrite carbonate evaporite at the base of this evaporite sequence. This is rock salt. What we did was we investigated the frictional properties of all of these different lithologies to try and understand how heterogeneous the strength, frictional strength of these different segments of fault would be, and to try and understand how prone these different lithologies would be to unstable or accelerating frictional slip. We did low velocity experiments, a typical rate and state friction, classical sort of earthquake mechanics type of approach, to try to understand the nucleation stage of earthquakes, the slow initial growth of a rupture which might ultimately become unstable. We looked at the scale dependence, and we also looked at, okay, once a rupture has grown, once big enough, of course, you get dynamic failure and very rapidly accelerating behavior, dynamic friction, and usually you'd expect some very strong weakening. We also investigated that. How do you do it? Well, there are no faults exposed in Groningen. It's all 3 kilometers under the ground. Some similar stuff comes up to the surface in the UK and Germany. Here's a lateral equivalent in the UK. You can see faults in the sandstone here, for example. Here's the sandstone. This is the carboniferous. You get in and look at these things. The faults themselves are remarkably planar, and most of the displacement is concentrated in very, very narrow slip zones, even far smaller than this 10 centimeter zone in here. Very, very narrow zones and discontinuities within the core of the fault. So that gives us a little bit of confidence that in direct shear friction experiments on thin layers of crushed up fault material, fault gouge, in a triaxial machine under in situ conditions would give us a sensible way of quantifying the frictional properties of these fault rocks, okay, the rocks that would be found in these faults in the field. Here's some typical results from Luc Kuhnfeld's PhD, friction coefficient against displacement for these different lithologies. Blue, the reservoir sandstone. Green is this anhydrite carbonate at the base of the evaporites. And the Tendur claystone, that's the claystone on top of the sandstone, and here's the substrate, the carboniferous. And by changing the velocity that we impose to measure the friction coefficient, we can see how sensitive the strength is to the velocity using this classical rate and state friction approach to quantify the rate dependence of friction. That's what we did. That's what Luc did for all of these different lithologies and for all kinds of mixtures. And he basically found something like this. This shows friction coefficient of all of these different lithologies and their mixtures. And this shows the rate dependence. This is a measure of the potential for accelerating seismic slip. Okay, so if this is negative, then slip can accelerate and you can get an earthquake developed. If it's positive, you do not expect that to happen. What you see is there's a very marked mechanical strength stratigraphy. So the carbonates at the top are very strong. The 10 Boer material is very weak, this clay-rich material. The sandstone is strong, friction coefficient of about 0.6. Carboniferous is clay-rich, it's weaker again. So you see this stratigraphy and a mixture, for example, of this carbonate anhydrite rock with the sandstone, that's this one, it's also very strong. Interestingly, all of these simulated fault rocks have got A minus B, this measure of potential for accelerating slip. It's all positive, except this basal sextine material at very low velocities and mixtures of this basal sextine, this carbonate anhydrite evaporite rock with the sandstone. Here it is. That gives you accelerating slip. So these are potentially, from the point of view of a rate and state friction model, these are potentially seismogenic materials, more so than the rest. Also looked what happens if you slide these fault rocks and then stop and just leave them under in situ conditions in a so-called slide hold slide experiment, a friction experiment where you slide the rock, you let it heal at in situ temperature, then you re-slide it and you measure the increase in friction coefficient. So here's increase in friction coefficient after healing for different amounts of time. Interesting thing is that the clay-rich rocks show absolutely no healing, no increase in strength with time. They remain weak. The sandstone increases quite strongly in strength, and this carbonate anhydrite basal evaporite increases very greatly. And these are the longest duration hold experiments ever done, actually, around 3 months. Of course, if you re-slide this material, the rock loses its strength. You get a bang. Okay, so this is also a measure of the seismogenic potential of these materials. It tells you again that the carbonate anhydrite at the bottom of the evaporites and the sandstones, they have potential to produce accelerating slip when you reactivate a fault in those materials. We also did very high velocity friction experiments. Some of you will have heard of this kind of work in association with work on natural earthquakes, doing extremely high velocity friction experiments where virtually all materials, if you slide them fast enough, they show a huge drop in friction coefficient to very low values around 0.1 or 0.2 because of processes like melting or producing silica gel layers or thermal pressurization of the pore fluid, many other effects. Do these effects occur in Groningen once you start a fault moving? We did similar tests, but with instead of huge displacements that you have in natural earthquake experiments, we did slip corresponding to a Groningen earthquake. So 10 or 20 centimeters of slip reaching a peak velocity of about 1 meter per second. That would roughly simulate a Groningen earthquake. We did them under relatively high normal stresses, which is unusual for this type of experiment. And we used the real gouge materials from the field to do these high velocity friction pulse experiments to simulate an earthquake. And what did we find? We found this kind of thing. See, we have a cylinder here with the crushed up rock in between here. We load it, and then we subject it to this very fast pulse going right up to 1 meter per second and down again in displacement of about 10 or 20, in this case 12 centimeters here, look. Displacement pulse of just 12 centimeters over in a fraction of a second. So it's a simulated earthquake, and what we found was this anhydrite carbonate rock on top of the reservoir, the top of the sequence, extremely strong, shows an enormous drop in strength. The sandstone also shows a substantial drop, So does the carboniferous material, the tin boor less so. Now, these are all exhibit some sort of slip weakening behavior after a peak strength. Then this type of behavior is capable of producing an earthquake because you have a drop in strength, which means you can get acceleration under a given load in a given elastic loading system. So this suggests very strongly that the basal zechstein again would be very sensitive to earthquakes, the Slottern too, and perhaps the carboniferous. These are preliminary results. We have to repeat these experiments because there are some discrepancies. But basically, the picture that emerges is here's the reservoir, especially on a fault where this material, this carbon, is dragged down here. This would have high potential for earthquakes. And this material itself, this carbonate anhydrite material at locations like this, or where it is actually juxtaposed against itself on a fault, has high potential for earthquakes. So it's a high friction coefficient for the basal zechstein, high friction coefficient for the sandstone, and that can dramatically drop when you have dynamic weakening. The other rock materials in between, their strength doesn't do too much. So that leads you to think that sandstone and the basal zechstein and mixtures, they are going to be the things which are very sensitive towards earthquakes. And indeed, this is a bit controversial and it's also very preliminary. Distribution of earthquakes recorded within the reservoir in the last few years suggests a bit of a skewing towards the top of the reservoir, which would be consistent with this anhydrite carbonate evaporite stuff and the sandstone being the most sensitive to initiating earthquakes. Does size matter? I have to cut corners here, otherwise I'm running out of time and Hadi is going to chop me off. To find out whether these tiny little samples actually produce reasonable results for friction, we did meter scale experiments in Japan at an earthquake science laboratory in Japan. And I won't show you the results. Take it from me. To our astonishment, we got, for the rate and state dependent friction behavior of these materials, we got exactly the same results in this monster machine with 1.5 meter size sandstone blocks sliding across each other as we did with the 5 centimeter assembly in the lab in Utrecht. The results of those friction data have been put by Luce Bowser in her PhD thesis into purely dynamic models of, as well as quasi-dynamic models of rupture modeling of earthquakes from producing earthquake waves. That's where it all ends up going. So, yeah, the end of the story now essentially is, I'm cutting lots of corners here, we've characterized the way the sandstone behaves. It has a substantial amount of plastic deformation, which is important for understanding the evolution of stress and strain. And we've got a much better description of the strength behavior of the faults and their earthquake, their proneness to earthquake generation, if you like. It's not over, there's still much to learn. And the DeepNL program, which is a Dutch national program from its research council, is a framework of ongoing research in which we continue to investigate these things. I think I must stop there.
Thank you very much, Chris. To be honest, I didn't notice the pass of time.
Oh, you're too kind.
I was so much absorbed to the whole story. It was really fascinating. And then I watched, oh, he has 10 minutes left in the whole. So that was really, really nice. So thanks very much. Without any further ado, I would like to pass on to Sebastian to chair the discussion. Well, thanks again.
Yeah, thank you, Hadi. Thank you, Chris, for a fantastic talk. Again, I've learned an awful lot. Before I take over some questions, I would like to give a shout out to the Danish Technical University. I was just informed there's an entire course watching your webinar live as we speak now. So you're lecturing for free at the
That's amazing. We received a photo from them. So all the students are now watching us live. So hi to Denmark. So that's great.
Well, that's very nice. There's no doubt Hamid Nick is watching from DTU up there in Denmark. Hello, everyone. I visited you not long ago.
We expect some questions from Denmark now that we have welcomed everyone. So let's start with the first question from Anne. Thank you, Chris. Very interesting. For the sandstone results, with the absence of stage 1, as you said, the field samples will not have microcracks affect mechanical behavior of stage 2 and 3.
So could you just, I didn't quite catch the question, actually, forgive me.
Sorry, I just put it back up here. It was perhaps too fast.
Yes.
For the sandstone results, with the absence of stage 1, as you said, the field samples will not have microcracks affect the mechanical behavior of stage 2 and 3.
So what we find is, I'm not sure if I'm answering your question quite as you mean it here, but if I understand you correctly, Anne, what we see is that if we subject our samples to hydrostatic pressures which are roughly equivalent to the mean stress that we believe exists in situ and has been measured in a few in situ measurements, right? If we take the sample to those hydrostatic stresses or mean stresses, then we see a dramatic stiffening of the sample. And from that point on, its behavior is quite different from mean stresses below the in situ mean stress. And on that basis, we infer that by subjecting the sample, by taking the sample up to roughly the in situ mean stress, we are closing cracks between the grains that have been introduced in extracting and handling the sample. Does that answer your question?
So we need to let Anne comment on this in the chat, because I'm just reading out her questions. So there's a follow-up question from Anne. Actually, a few questions around the same topic. So she also asked, did you check if the clay on the grain boundaries was present and not compacted in the undeformed twin?
Yes, so we know that the samples that we compared in that one graph I showed you, for example, they are really indistinguishable before you start. And when you conduct this experiment, you do simply see that despite the cycling behavior, the strength envelope for the cycled and the monotonically loaded samples, they're just exactly the same. So that tells you that the procedure does not introduce more damage. And it also supports the argument, the idea that that initial hydrostatic loading phase removes the core damage, for want of a better word, and that once you get up into stage 2, then you're looking at something very close to the real in situ behavior.
Okay. Thank you. So one of our previous speakers, Mark Bentley, is asking a related question and would like to confirm if the grains are not breaking. That suggests that the compaction will stop once the low volume of clay has compressed. Is that correct?
Sorry, I'm having a little trouble here in, I rather, yeah, with my screen.
Yeah,
so that distracted me again, I'm afraid. Can you, can I remove my presentation from shared screen or not?
Please.
It's already removed from the shared screen.
Okay. Oh yeah, that's
so.
Yeah, I sort of had.
Not breaking. That suggests that the compaction will stop once the low volume of clay has compressed. Is that correct?
Yeah, basically what you see indeed is a transition between stages 2 and 3 from this linear behavior where compaction of the clay films dominates the inelastic behavior to the onset of microcracking. And that is in effect the onset of failure of the sample, and you get a macroscopic yield behavior of the sample and a load drop, and that correlates exactly with the onset of microcracking. And up until that point, the only thing that you see is this compression of these clay layers.
There's a couple of questions from Sarah, and they're about production, and she asked, would the seismicity stop after the field is shut in? And then related to this, and is there a way to keep producing and manage seismicity?
So the question about, will seismicity stop when production stops, Sarah, that is the big question. So, let me give you a little background on that. Of course, people living in Groningen are very upset about these earthquakes. It damages their homes. It introduces a risk that is not natural. It's not an act of God. It's, an act of a company. People are very unhappy about it. And intuitively, of course, people imagine that if you reduce or stop production, that earthquakes will stop. Production has been reduced, especially in the center of the field where most of the earthquakes are occurring. And the frequency and magnitude, the frequency of earthquakes has decreased. The magnitude, to some extent, perhaps, it's not enough data to tell. This morning there was a magnitude 2 earthquake in that region, even though production there has actually ceased in that particular part of the field. So there have been several magnitude 3.4 earthquakes since production has been stopped in those in the central part of the field. The big question is now, of course, if production is totally stopped, which is now scheduled for 2022, with 20% of the reserve still in place, if production is totally stopped, will the earthquakes continue? And of course, very probably not is the answer to that, in my opinion, for several reasons. There is a time-dependent effect, which I didn't talk about today. So there is a rate sensitivity of compaction of the reservoir. So you will get a certain amount of ongoing creep in the reservoir, which will continue to perturb the stress field around faults. We are currently investigating the creep behavior. Even if there isn't creep behavior in the reservoir, the stress transfer to the surrounding formations, of course, means that you'll get some heterogeneous loading of the formations around. Some of those may show time-dependent effects, or there may be creep on faults. Now, there is a school of thought that says, well, if you have creep on the faults, then the stresses will be relieved on the faults, and that will reduce the potential for earthquakes. But, of course, that may be true for certain segments of the fault. As you've seen, strength is highly heterogeneous along these faults, along different rock types. So again, there'll be transfer of stress between different portions of the fault with different creep resistance. So it's perfectly possible that you will change the pattern of earthquakes, the evolution of the earthquake activity. But it's very difficult to say at present what that would be. You may have simply fewer and fewer and fewer earthquakes with lower and lower magnitude, but you may also have fewer earthquakes and then suddenly a larger one. So I think most people who are really working on this acknowledge that it's very unlikely that earthquakes will stop when production stops. If you wait long enough, yes, it will return to its natural equilibrium, if you like, and earthquakes will stop. The big question, Sarah, is how long is that going to take? Is it 2 years? Is it 20 years? Is it 200 years? Can you do anything about it? There have been all sorts of ideas about injecting gases to, sort of reflate the field and so on. These are all very tricky matters because, of course, if you start playing around, if the company producing the gas was to start playing around in there and actually, it's a highly complex natural system, very difficult to predict what happens. Very hard to say. So it's an extremely risky strategy, but I'm happy to say that Hadi and myself and our colleagues are involved in a research project on just that.
Thank you very much. There are so many questions coming in at the moment. I just don't know where to start because I think every great answer triggers another
500 questions.
Let's take this one from Miles Wilson because he talked about earthquakes. Thank you, Chris, for the interesting talk. how constrained are the recorded earthquake locations? They seem a key method for possibly ground truthing the faulting lab experiment results.
It's a wonderful point, Miles. Spot on. For the question, there are now 65 seismometers placed in that region, which is about 30 by 30 kilometers. Okay, so it's pretty densely instrumented now. With some very, very fancy processing techniques developed by the Dutch Meteorological and Seismological Institute, and by Shell and NAM, and by Cambridge University, they feel that they can locate these events now, the small events, to within 20, 50 meters, something like that. In the past, there was like 800 meters uncertainty vertically. Now the location is believed to be pretty accurate. There's still some discussion about that, but there is a very, very clear alignment between the locations, the recent locations, which are relatively accurate, and the faults. So there's no question anymore. These are occurring on faults. What was the rest of the question? Sorry, I got a bit carried away there. Oh, yeah. And yes, indeed. So what one wants to be able to do, of course, is see, well, right, are these earthquakes really occurring where we have these seismogenically prone formations, where we know the stress will be elevated towards forcing an earthquake because of the offset on the fault, for example. So accurate locations, in principle, could tell us if our sort of mechanical understanding so far is right. And that is exactly also what is going on at the moment. We are trying to bring these things together. We're trying to marry together the geophysical observations and the geomechanics and geomechanical modeling.
Thank you, Chris. I'm going to take a question from Kishan Kumar, who's conscious of time, and I do apologize profusely if I can't get to everyone's question as part of the webinar. But Kishan asked a question that someone else has asked, I think, in a very similar form, which is, again, thanking you for the talk. When you mention inelastic strains, do you think creep and thermal strains also affect the porosity change considerably? Someone else asked about other mechanisms that could help to dissipate energy in the reservoir.
Right. So the temperature within the reservoir region is very stable. So there are no significant thermoelastic effects. Okay. But creep, yes, we have very clear evidence that the compaction behavior of the reservoir has a rate sensitivity. It's relatively minor at the faster rates in the lab. So the rate effects that you see in the lab at sort of measurable laboratory deformation rates are pretty small. If you were to translate it into strength, let's imagine, like, how much would the strength envelope of these sandstones shrink if you were to do the experiments that we have done at strain rates which would correspond to depleting the reservoir over 50 years, then it might change the strength by 5 to 10% or something like that. So those rate effects are there, but they're not very large. What is really the big question is the much longer term creep behavior. So if you shut down the field, then you have to think over periods, of tens of years, maybe hundreds of years, you might get into different mechanisms then. So we're trying to understand the mechanisms of creep. And there seem to be a combination of time-dependent slip on these clay films with, at high stresses, some very, very slow microcracking processes which are time-dependent, stress corrosion.
Great. Thank you very much, Chris. I'm going to hand over to Hadi now for some closing remarks. Again, apologies that I couldn't take all the questions that have been asked in the chat room. I think it was a fantastic talk that really nicely illustrates some absolutely fundamental science, how
Thank you.
amounts of clay impact creep behavior helped us to understand a really difficult real-world problem that has huge economic and societal consequences. So absolutely fascinating. Thank you much, Chris.
Well, thank you for the compliment. I enjoyed myself, and forgive me for talking too much.
No. Hadi, over to you for some final
thanks
comments.
a lot. As I said, I didn't notice it was just 10 minutes before the end of the talk, so that, I mean, the whole event. So that was really, really informative. Thanks again, Chris. I would like to take the chance to announce our next week's speaker. Our next speaker will be Charlotte Adams. Charlotte is from the Coal Authority of the UK government. She will speak about using abandoned mines to decarbonize heat. So please, until next week, the same time, 4 p.m. Central European time zone, stay happy, healthy, and tuned. And we all see you next week again with yet another exciting geoscience and geoenergy webinar. Thank you all, and goodbye.
Thank you, everyone.
You had some
Thank you very much. It was a pleasure. It's good to see you, Sebastian. It's been a long time.